All right, welcome class. We're here in another week thinking about phase transitions in the Ising model. We've been on a bit of a journey trying to find approximate solutions to uncover the truths that we know the that the Ising model contains, notions of symmetry and universality. We've uncovered some things like the fact that even using a mean field theory, we can predict spontaneous symmetry breaking, and that due to how quickly fluctuations grow in high dimensions relative to correlations, that actually mean field theory works really well to uncover those universal behaviors, those critical exponents in high dimensions. And unfortunately, we also learned that in 3 and lower dimensions, that fluctuations are always really important. If we get arbitrarily close to the critical point, those will dominate any expectation. So as always, we'll first kind of remind ourselves of some of those key points. We'll review how we constructed that mean field theory a bit rigorously and how we convinced ourselves that indeed dimensionality plays a really important role, and that a dimensionality of 4 is special in terms of how it sets the scale for whether or not fluctuation corrections are important. This will lead us into a alternative way to try to formulate an approximate solution using a variational principle or variational construction for the free energy. What we'll find is, as before, that even variational statements don't work all that well. That really we need a completely novel sort of approach for tackling critical behavior. And that will bring us finally to a discussion of something called the renormalization group, something I've alluded to previously in lecture and in the live sessions. And we'll sketch out the basic idea there and then actually show how it works in the next lecture. Okay, so that all being said, we identified pretty quickly from our mean field theory that what such a theory and an approximation really was neglecting was correlations. That by looking at the influence on a tagged spin of the average environment, there was no mechanism, therefore, for the tagged spin to influence that tagged environment. So those correlations, something we've measured by introducing a correlation, or quantified by introducing a correlation function, Cij, which was the fluctuation in spin I, fluctuation in spin j, averaged, which can be written as the average of Si Sj less the average of Si times the average of Sj. This was something which is strictly 0 if spins I and j are uncorrelated, and the extent to which it is non-zero tells us about how much influence those spins have on each other's statistics. I didn't prove for you, but told you that this correlation function had a specific form with some function that depends on dimensionality that decays over a characteristic scale C, the correlation length. And had a power law dependence that decreases as a power d minus 2 plus some eta, that eta being the anomalous dimensionality. Essentially what this function looks like is that it depends on the distance between spins I and j. We don't expect it to depend on the direction that that vector points in. We argue that it starts at 1 minus m squared, and away from the critical point should decay, and it decays with some, let's try that again, decays with some characteristic scale, that correlation length. And what makes critical points exceptional is, in fact, that those correlation lengths, the length scales over which spins influence each other, diverges. It diverges in a particular way as a power law with some critical exponent, where that critical exponent in mean field theory was a half in 3 dimensions, is 0.63. So indeed, so this is what mean field theory is neglecting. It doesn't have a sense of correlated spins. And we saw exactly how to write down mean field theory in such a way that in principle we could correct for it. But those corrections, at least simple approximate treatments of those corrections, don't work. For example, we formulated a thermodynamic or free energy perturbation theory. For the Ising model, this took a form of a constant plus our mean field with some H effective and a correction that was exactly due to the fluctuations in the spins. By taking these two terms as a reference and identifying those fluctuations as a correction, we showed how you can write the partition function in the full system, the exact Ising model canonical partition function, as a mean field piece times a specific average of that correction, and Boltzmann factor of the delta E that we neglect in the mean field theory, averaged in an ensemble described by the mean field system. Just to be concrete, the partition function of the mean field system is the sum over all the spins weighted just by that mean field part of the energy. There is an exact equation for the corresponding free energy, as free energies and partition functions are always related to each other, in which case we have a sum of the mean field part of the free energy plus kBT log that exponential average. And our perturbation theory essentially consisted of trying to approximate this at some low order expansion in that expectation value. So to first order, the correction is just the average of the energy. Something we found was 0. And to second order, add minus beta by 2, the fluctuations in delta E, which we could write out and was given by a sum over a bunch of indices and a bunch of corresponding fluctuations, something that diverges near the critical point, thus not really being perturbative. In fact, we noted also that that is something that one might not in general be able to neglect because it is a strictly negative contribution to the free energy. So before we go on past this free energy, this thermodynamic perturbation theory, I want to step through the calculation which we worked through last time that tells us when exactly we can neglect those correlated contributions to the free energy, which is not because they contribute only positively to the free energy, but rather it's a question of when their contribution is small relative to the mean field contribution. So the argument we laid out before was that we should be able to neglect those correlations when the contributions we've kept, things that go like the mean squared, are much larger than those that go like the fluctuations in that spin. We had to think through how exactly to estimate these two contributions. To estimate them, we decided to consider the fluctuations as an average over a correlation function, averaged in a volume of size set by the correlation length. And noting what the form of that correlation function is, again, not something we've derived in this class, but can be derived. We have the factor of the volume, which goes like the correlation length to the d. We have some solid angle for noting the rotational symmetry associated with that correlation function. We have an integral over the volume, and then a Jacobian for a d-dimensional system. This yd function and the power law portion with anomalous exponent that within the mean field theory is equal to 0. So again, what we are shooting for is really a question of self-consistency. We have this term estimated in mean field theory. We are working out a way of estimating the second term in mean field theory. For mean field theory to be self-consistent, we can ask if the components we've included are larger than the components we've neglected. This does not necessarily tell us what the correct answer will be, but it would tell us that at least the approximations we've made are internally consistent at the level of theory we're considering them. All right, so those integrals would require knowing precisely that function yd. Rather than doing that, we can get effectively the scaling of this integral with temperature by factoring out the temperature-dependent contribution due to the correlation length. So by letting u equal r in units of the correlation length, and thus du is dr over that correlation length, we can make that substitution. We'll have that solid angle, the volume of the correlation length. We'll get a volume of that correlation length when we substitute in r to the d minus 1 times dr. When we make the substitution, we will also pull out a factor of that correlation length to the d minus 2. And we will have left over an integral over du from 0 to infinity u y d u through approximating the top hand part of that integral is to infinity. So this is some number. It's an integral that if we knew the form of y of d, we could compute, call it b. That factor of correlation length to d cancels that factor of correlation length to the d. Yielding altogether this constant b, the solid angle, and the correlation length to the 2 minus d. I'm just flipping that denominator upside down. So we also know how to estimate the average of S squared, and we can conveniently express it also as the correlation length by noting that the correlation length goes like some basic unit of length, call it C naught, to the T minus TC over TC to its anomalous critical exponent nu. We know that average of S is what we've meant by M, which is equal to, in mean field theory, T minus TC over TC to the 1/2, or more generally, to the exponent beta. Squaring M, thus scales like T minus TC to the 2 beta. Beta in mean field theory is 1/2, as is nu. So they both scale with temperature in the same way. So M squared is going to be proportional to the correlation length to the -2. I can define that constant of proportionality as the bare correlation length, like so. And thus the condition of self-consistency of S squared being greater than fluctuations of S squared boils down to when is the bare correlation length squared times the correlation length inverse and squared greater than B times the solid angle, the bare correlation length to the D minus 2 times the correlation length to the minus D minus 2, or rearranging, when is the correlation length to the D minus 4 greater than B times the solid angle over the bare correlation length to the 4 minus D. And as noted last lecture, as T goes to TC, that correlation length diverges. That's what endows the susceptibility with the divergence, what allows for singular responses generally. If D is greater than 4, then the left-hand side of that inequality close to the critical point will be infinitely big. And so as long as D is greater than 4, the inequality is always going to be satisfied if we look close enough to TC. However, for the same reason, if we look close enough to TC and D is less than 4, that would make the left-hand side scale as 1 over the correlation length, which would go to 0. The right-hand side is strictly positive, so eventually close enough to the critical point, 0 is going to be smaller than the right-hand side, invalidating that inequality. So what we learn from this, apart from uncovering why D is so special, is really that fluctuations don't grow as fast as averages and D is greater than 4. And thus, really that mean field perspective is the right one. It dominates the expectation values. So if you think about that in a physical perspective, if I have my tagged spin, it interacts with some neighbors. The numbers of neighbors that it interacts with depends on dimensionality. If we take a limit where the dimensionality is really, really long, there's so many neighbors that you could imagine even making central limit theorem like arguments that says that the typical behavior is all you see. In the limit that I have an infinite number of neighbors, that distribution would likely become very sharply peaked. I would only ever see the typical environment, the typical, the average environment, because I have so many neighbors that I have a self-averaging in D is greater than 4, dimensionality of 4 is essentially close enough. I have enough neighbors that those factors dominate over any fluctuations around that average. That doesn't mean that mean field theory is useless. 4D is less than 4. Mean field theory is a good description as long as those fluctuations are negligible. And we can define a temperature, call it Tg. Excuse me. Where we have an equality between the contributions from fluctuations and means, which would yield B times that solid angle to the 1 over D minus 4 divided by the bare correlation length. That temperature is known as a Ginzburg temperature. Which sets the proximity to the critical point where fluctuations cannot be ignored. So, in fact, if you were to measure critical scaling of, say, a liquid vapor transition, close, but not so close to the critical temperature, the exponent would look apparently like that predicted by mean field theory in our typical three-dimensional systems. As we get closer to the critical point, we would start to notice deviations from that mean field behavior, which are due to fluctuations, due to these correlations neglected in our mean field approximation. How close we can get to the critical point before we notice deviations from mean field behavior is quantified by this Ginzburg temperature and is essentially set by the bare correlation length. So how correlated do molecules or spins start? So apart from observing that there is this critical point, there is this Ginzburg temperature, and there's a special role that D is equal to 4 plays. An unfortunate thing that we learned is that perturbation theories, attempts to correct with small parameters our mean field theory, aren't going to work, and D is less than 4. And so this is where we'll begin a little discussion on how to cast interacting problems as variational problems. How we'll develop a variational theory for approximating partition functions in free energies. Okay. So to start, let's note that exponentials, things that pop up all the time in statistical mechanics, have really nice properties. So both e to the x and e to the minus x are convex everywhere. It means that if I was to look at the function e to the x, it is always greater than or equal to its tangent curves. If I take a tangent curve at 0, that would mean that it is greater than 1 plus x. Analogously, e to the minus x is always greater than or equal to 1 minus x. One can see this graphically. So e to the x might look something like that. E to the minus x might look something like this. And if I took a tangent curve, say at the origin, it would look like so. Or a tangent curve for e to the minus x, look like that. And indeed, the black lines are greater than or equal to the red dashed lines. This being the red dashed line. What that means is if I have a fluctuating quantity, let's for simplicity imagine that it has mean 0. Then the convexity of the exponential implies that e to the plus or minus x averaged is always greater than or equal to 1. If we let x equal some change in energy less its average, evaluated in some knot ensemble, that is a quantity which has mean 0 by construction. Then using this inequality, we would find that e to the minus beta delta E averaged in the knot ensemble is greater than or equal to e to the minus beta average delta E. Plugging in our definition or our relationship for x and noting that an average inside an average is just a constant, so I can move it to the other side. Now, that delta E, for example, could be the delta E, our correction from our mean field theory, in which case we would have a bound on the partition function as a product of the mean field partition function or any reference partition function, and e to the minus beta, the average energy in that reference. These statements of convexity are known as Jensen's inequalities. This mathematical structure then lends itself to a variational theorem. Imagine we have a reference system. Parameterized by some set of variables. Let's call those variables the vector A, which could be some A naught, some A1, some set of variables. The best estimate of Q, the partition function in the full system, given a reference system parameterized by a set of variables, will be those parameters which maximize the product of Q naught, the partition function in that reference, and that exponential factor of the average energy difference in that reference ensemble. i.e., if we took derivatives with respect to each one of those parameters of log of the reference partition function less beta delta E in that reference, those parameters which satisfy that equality will give us the best estimate of our partition function. So it's natural, given this new structure, to ask, can we use this theory to get a better estimate for the Ising model in 3 dimensions, for example? All right, so how could we do that? So notice we have to be able to evaluate 2 quantities and their derivatives to employ this theory. We need to be able to evaluate the partition function in this reference, in addition to the average energy in that reference. So we essentially only know how to compute quantities if we have non-interacting systems. So let's try to find the optimal non-interacting system to employ this variational theory with. So let's try a reference, which is some factor minus h naught multiplying the sum of the spins. So this h is a parameter we can try to optimize. All right, within that reference system, we'll need to compute the partition function and the change in the energy on average. So delta E on average is going to be E of the Ising model averaged in that reference less E of that reference averaged in the reference. So the Ising model has the minus J sum over spins SI Sj. It has the minus H sum over single spins. And now we have a minus is a plus. Our reference energy. Now these are averaged. Now note that this is a single spin energy. The spins are independent. So we'd be averaging each in that double sum independently. All right, so then we can compute all of those, setting as we normally do the average of the spin as equal to m. This term would be h naught. I have n spins. Let's call it m naught for the average magnetization in that new reference. I have a minus h n m naught. Here I have something that's going to go like m naught squared, a minus j, and however many spins are in that, or how many of terms are in that double sum, that's n times z by 2. We also know how to compute the partition function. We've done this a couple times already. Log of q naught is going to be, we're going to factorize the partition functions because they're independent spins, and we'll end up with n factors of the single spin partition function, which is just log of twice hyperbolic cosine of beta h naught. So those are our two terms. In order to get a the best variationally speaking estimate of the partition function, we need to find an extremum with respect to our variational parameter h naught. So that's computable by dh naught, log of q naught minus beta average energy difference naught is equal to 0. All right. Now, here's a trick. If I take the derivative of log of the partition function with respect to h naught, I will get the magnetization. H is conjugate to the total magnetization. So up to a factor of beta, that's the first term. Now I have to take the derivative with respect to beta times the average energy difference, which is here. Let me go ahead and note that little trick. So d log Q dH. So if I was to put H in the denominator, indeed that would have been N times the single particle magnetization. Okay, so now I'm going to have a minus beta derivative of average of delta E. So I'll get N. So M naught depends on H naught, the average magnetization in the independent spin system still depends on the strength of that magnetization, that's external field. So I'll get a minus J in Z in M naught and a D M naught DH naught as one term. I'll get a minus, I have a H N D M naught D H naught. And a plus in, should not forget my betas, beta. From the last term in the top line, I have an N M naught plus a beta in H naught D M naught DH naught. This all needs to equal 0. All right, so let's see how this is going to simplify. So I have N's and betas everywhere. So that will, if I get rid of all of those, I'll have a M naught plus a J Z, sorry, I get the betas, J Z M naught D M naught D H naught. I have a plus H D M naught D H naught. I have a minus M naught and a minus H naught D M naught D H naught. All 0. All right, what else can I do? So I have an M naught here and minus there. Every term now has a derivative d M naught d H naught, so all of those can go. And I'm then left with H naught should be J Z M naught plus H. Look at that. Where have we seen that before? That's exactly what we actually used in our mean field theory. That was what we had called, at that point, H effective. So in fact, through intuition, we had picked the variationally optimal effective field. In fact, somehow, in some sense, we already knew this. since when we explicitly worked out the first order correction, it was 0. Through perturbation theory, if we're at an extremum, making a small change does not change our answer. So a first order correction to our mean field theory vanish, that is a statement of variationally optimum. You could imagine constructing a slightly more complicated ansatz for a reference system. Say that the energy was minus the sum of the spins, each with their own field. That would be a single particle problem we could still solve, but that we'd have an extensive number of parameters. Indeed, that is one way to derive that correlation length within mean field. However, if we did that, we would still get the same critical exponents. So it's not worth the trouble. All of this points to a really radically different approach we need to take. So the remainder of our discussion of the Ising model will consist of two distinct approaches, which actually are quite successful. One is a analytic approach, the renormalization group. The other is a numerical approach, Monte Carlo simulation. I want to, we'll spend the next 2 lectures talking about the renormalization group and then get into Monte Carlo simulations. But before I do, I want to show you what the Ising model actually looks like numerically, because that will actually give us some insight into why the renormalization group will work and why it was motivated to begin with. So let me pull a simulation up. Okay, so this is a simulation, a lattice of a 100 by 100 Ising model. I've colored up spins blue and down spins green. I've reminded you what the phase diagram looks like in the magnetization and temperature plane. We know a regular old Ising model has a magnetization that is finite at low temperature, could be finite and positive or finite and negative. As we approach the critical temperature, the magnetization goes to 0. It does so with a critical exponent, corresponding power law. What you probably don't have much intuition for is what it actually looks like. So if we actually simulated the Ising model, advanced a Monte Carlo simulation, whereby I construct a routine to sample configurations in proportion to their Boltzmann distribution, something we will elaborate on in a week, this is what you'd see. So for temperatures above the critical temperature, different snapshots look like this. There's no long-range pattern. I have equal numbers of spins up and down. This is, of course, at no applied field. There's no big macroscopic domains of spins up or spins down. And there's no long-lived patterns. So this is the mixed state, the 0 magnetization state, and what you'd expect to see well above the critical point. If instead I took the lattice and I cooled it down This is a couple loops through our Monte Carlo algorithm that started in that same high temperature state and is now cooled. What you would see as you continue to advance the calculation is that big domains are stable, but only one domain is eventually observed. So if we do that again, if we started at a high temperature, at low temperature below the critical point, we expect to see a predominant number of spins up or down. This is the symmetry breaking, whereby the system spontaneously chooses whether or not to go all up, like it has here, or correspondingly all down. That doesn't mean that there aren't fluctuations still. In fact, you can see them. There are little islands of green that have characteristic sizes. Those are the correlation, computable from the correlation lengths. But, at colder temperature, the characteristic sizes would be smaller and smaller. We could put the system at coexistence, so keep the total number of spins up and down constant. And if we're below the critical point, what we would see is an interface separating spins up and spins down, just like you'd expect to see with a liquid in coexistence with its vapor. Again, that doesn't mean that there aren't fluctuations. If we involve the algorithm, you would see fluctuations of the interface. However, below the critical point, that interface is stable. Again, it doesn't mean that there are no up spins in the predominantly down spin state or down spins in the predominantly up spin part of the system, but they're small, isolated, and not many in number. This is both to be contrasted with what happens at the critical point. At the critical point, if we started with a random assortment of spins and propagated the system, at the critical point, the correlation length diverges. So we find patterns on all scales. There are big domains and small domains. There are middle-sized domains and domains that will fluctuate and span the whole system only to be killed off again. In no simple terms, it is chaos. It is complicated. It is fluctuation dominated. That doesn't mean, however, that there aren't some patterns. As was alluded to in the live sessions, at the critical point, the fact that there is no characteristic scale means that the system is scale invariant. In fact, I can view it at the critical point at different sizes, at different levels of resolution, and the system looks the same. There's a really nice YouTube video done by a friend of mine, Doug Ashton, that illustrates this point. So the link is there if you want to look at it again. What I will show you now are different size Ising models, with spin up being black, spin down being white, with very large lattices at the critical point. Now, if what I said is true, that at the critical point there's a scale invariance, it should very strictly mean that each system size looks identical. And this is really well illustrated in this video. In fact, one could take those and put them in reference to each other and find patterns that correspond everywhere. Indeed, that's the self-similarity of the critical point. Because fluctuations exist on all scales, there are large domains, there are small domains, there are mid-sized domains. If I looked at a small lattice, I will see all of those characteristic scales. If I looked at a large lattice, I would see all of those characteristic scales, as well as new scales that are enabled by being on a larger lattice. So I can, and was just demonstrated, I'll play it again just because it's so cool. That really means, in a very strict sense, that the self-similar nature of the lattices means that I can take a snapshot and I can zoom it back in or out and find corresponding patterns at every length scale. So this is no gimmick. This is just running an Ising model, stopping and taking a snapshot after an arbitrary number of steps in this Monte Carlo algorithm, and demonstrating that indeed one can find those self-similar patterns. Okay, so that's what the Ising model looks like. And that's an important characteristic of the specific thermodynamic point that we've really been concerned with. Finally, we found some potential simplicity associated with describing the system at the critical point. And that's concerned with this self-similarity. The fact that there is this fractal nature maybe gives rise to a way of calculating properties of that critical system. And this is indeed what is formalized in the theory of the renormalization group. It's a theory that dates back to Leo Kadanoff, Michael Fisher, and Kevin Wilson, the latter of whom won a Nobel Prize for it. Kadanoff and Fisher were the first to think about that in the context of the Ising model before Wilson formalized it a little more generally. Wilson was coming from high energy physics, where he was running into alternative sorts of divergences and difficulties associated with taming them with standard theoretical tricks. And the basic physics, before we get into the calculation, is to note that there's a correspondence upon approaching the critical point between temperature and distance. Okay, so let's see how that would go. So let's start by drawing some snapshots of what the Ising model looks like at different temperatures. Okay, 5 little boxes. Let's start at some temperature T0, which is less than T1, something fairly cold. So imagine that most of the system is in some spin-up state, and that state is denoted by white. There will be, even in that predominantly spin-up state, fluctuations, as we've just seen, and there will be a characteristic size of those fluctuations computable by knowing the correlation length. If we increased the temperature to T1, the size of correlations in our predominantly up state will grow. It'll be more probable to have a larger fluctuation. There will still be smaller fluctuations also, but the correlation length is going to grow. So as we increase the temperature, the correlation length below the critical temperature increases. If we were at very high temperature, some T3, which is greater than T2, we have spins up and down, so the background is equally likely for every individual spin to be up or down, and we'll have some fluctuations, but those fluctuations will be small in size. If we look at some T2 greater than TC, well, if it's greater than TC, there's no long-range order. The system is predominantly mixed, but the scale of fluctuations will increase a little bit. The fact that it's a little bit colder will make it a little bit more favorable for neighboring spins to aggregate into specific size fluctuations. So that correlation length will increase. So for high temperatures, the correlation length increases as I decrease the temperature. At T is equal to Tc, we've noted that there are fluctuations on all sizes, so this looks a bit of a mess. And the correlation length diverges. Okay, so there's a correspondence in the correlation length increasing when we start at low temperature and increase the temperature, and increasing as we decrease the temperature at high temperature. Now consider what happens if we took the system at low temperature and we zoomed in a little bit. So imagine we picked this spot right here and zoomed in. Well, most of the system would be spin up still, but that little fluctuation we had now would look like it's slightly bigger. In fact, if we zoomed in, it would look like it's at a slightly higher temperature. Because there's this correspondence with increasing correlation length with increasing temperature, if we viewed the system on a different scale, it would look like we've changed the temperature. If the system was big enough that I couldn't tell the discrete lattice size, and I just looked at these fluctuations, and it gave you two pictures, one with a large correlation length and one with a small correlation length, again, you couldn't tell the scale of the underlying lattice, you would pick the system with a larger fluctuation and associate it with a higher temperature. The same is true at high temperature. If we took a snapshot and zoomed in, well, the system is still mixed, so there's a big gray background with every spin being equally likely to be up or down. But now the system would look like it was at a slightly colder temperature. Again, because there's a correspondence at high temperature with decreasing the temperature and increasing the correlation length. So if I just zoomed in, if I change the physical scale of the system, it would appear as if I've changed the temperature. Now this is different at the critical point, as we just illustrated with that nice YouTube video. If I zoomed in at the critical point, it looks the same. It's invariant to the scale over which I look at it. So the key insight of the renormalization group is just that a system at criticality is scale invariant and we can use this notion of finding scale invariance, of leveraging a relationship between spatial scale and temperature as a analytical routine to find where critical points are in models and to uncover their essential consequences. That's kind of vague. To understand exactly how we can use this idea, let's consider the Ising model in one dimension at zero field. So in one dimension, I have spins that sit on the points of a lattice. Like so. Call that spin 1, spin 2, spin 3, spin 4, spin 5, spin 6. There's a length scale associated with those spins, call it L. That's the lattice spacing in one dimension. We could imagine changing the scale of the system by viewing only half of the spins. Namely, we can take our original lattice and try to integrate out or sum over half of the spins present. So, for example, we could imagine taking the even spins, summing over their contributions to the partition function, such that we would get back a lattice that now looks like it's on a slightly larger scale. But other than that factoring out of spatial scale, it looks just like the original Ising model we had before. There's a bunch of spins on a lattice. If I hadn't numbered them already or told you what the underlying kind of original lattice scale was, you wouldn't be able to differentiate this picture from that picture. They look the same. So that's the idea, is to try to work out or quantify mathematically a way of changing scale, viewing an Ising model on different scales. And one way to do that operationally would be to imagine getting rid of some number, decimating some number of spins in such a way that, having done so, you return back a model that looks just like what you had before. So what would that actually mean mathematically? So we know our partition function is a sum over all of the spins, e to the, let's define a parameter k that in one dimension multiplies the double sum si plus 1, where this k is beta j. We could write that partition function sum as a sum over S1, a sum over S3, S5, all the odd spins, move all the even spins here, like so. This term here is some new function. After I complete the sum, it will be functionally independent of the even spins. So it will be some function that depends on just the odd spins. So the name of the game in the renormalization group will be to try to compute that function and see if it can be rewritten as the same form of the partition function we had before. And if it does, the intuition is that it should look like the model we had previously, only at a slightly different temperature. Namely, we could ask, let's give myself just a little more space. Whoa, no. Can we compute that function and make it look like that form? Namely, what we had in the argument of the exponential under the full spin sum, only with a new coupling strength. And if we could do that, then potentially we could iterate that procedure and find the points whereby getting rid of half its spins, changing scales, returns back a function that looks like it's at the same temperature. Another way to say that is we could try to iterate this procedure and find the fixed points of the map that we create by decimating half of the spins or changing the scale. So next lecture, we will do that explicitly for both the one-dimensional and two-dimensional Ising models and find that actually we get pretty interesting results. It works pretty well. So stay tuned for that. And I'll look forward to seeing you all in the live session. All right.